Okay, morning everyone. I'm Thomas. My topic will be robot navigation and mapping. So firstly, what is mapping? Mapping is using sensor data to create a spatial representation of the physical world so that we can use it either to explore or to learn more about our environments. There are a few different types of algorithms. In the 70s and 80s, we started with binary occupancy grids, and these are pretty much exactly what they sound like. So we have some sensor, and that sensor says something is here, and we believe it completely. And we mark that grid in a little map as occupied, and we go on our merry ways. Modern approaches use a more probabilistic approach, where we say, well, the sensor says something is here, but do I trust it? Should I trust it? Is the sensor even giving me correct information? And then based on all of that, we can figure out, is something actually here or not? So what types of sensors do we use? The first and one that I think everyone thinks of is a LiDAR sensor. So these are extremely accurate, but they only work in a single plane and they are extremely expensive. So in my university days, I had to make one of these robots and my LiDAR sensor set me back about 3,000 Rand, and that's the very, very low end. As these robots get a little more technical, these sensors will cost you tens and tens and tens of thousands because the accuracy is that important. But commercial robots, like you might think of little robot vacuums, they use cameras. And if you use a certain amount of cameras, you can extract depth information and then construct a map. So the algorithm that we use is called SLAM, which stands for simultaneous localization and mapping. So localization is really important. We can't build a map while moving without knowing where we are within this map. And how we get localization is done through a whole bunch of sensor fusion. So for example, you can be getting wheel data from your wheels, and your right wheel might say, hey, look, I've moved forward 5 rotations. And your left wheel might say, hey, look, I've moved forward 4 rotations. But they've actually both moved forward the same amount of rotations. So now your robot thinks it's on the other side of the room, but it's actually here. So it's really important to try to solve this. And how we solve this is with sensor fusion. So we might say, we've got a little scan of our room. The distance between this scan and the previous scan was, let's say, 5 meters forward, but our wheels are saying we went 5 meters forward and 2 meters left, and we can kind of extrapolate to somewhere in the middle. SLAM uses a front end and a back end. So the front end does a lot of the sensor fusion stuff that I've spoke about, where it takes our sensor data, it determines, what should we give to the back to process. So if you're using a scan, for example, you might say, hey, look, it's technically not possible for me to get a point within me, so that's probably not true. This then gets to the back end, which does a whole bunch of really fancy maths, and you get a nice little map at the output. What it does output is also an occupancy grid, but it's not a binary occupancy grid. It's a probabilistic grid, where each cell in this grid is a probability that something does exist in that cell. And then your navigation algorithm will determine at what probability level do we actually think that something's there, or are we willing to risk something being there. So VSLAM. VSLAM is visual SLAM. Very, very, very common for low-cost commercial applications, simply because it is so cheap to do. It's also got the really big benefit that because so many companies have made this, it's really easy for you to buy a few cameras and do it yourself. But you're sacrificing your accuracy. And the second big option is LiDAR SLAM. Much more expensive, much more accurate. And it gets so much worse if you translate this into the 3D plane, because LiDAR sensors are 2D only. And this is a big struggle that self-driving cars kind of have to deal with. You can kind of imagine if you've got a sensor spinning around, it's taking several thousand points per revolution just in one plane. And now we're making it an entire sphere. You've got tens and tens and tens of thousands of points. And to process this all in real time is immense. Navigation is actually fairly simple once you've got the map. So we've got a grid, and all that we're doing is we're saying, how do we go from here to here? And because our grid is essentially graph, we can use graph-based methods. So like Dijkstra or A* searches. On the top right, you can see what happens if one of your sensor readings is off and we're not adjusting for it. So in that scenario, we had a map, but we really didn't know where the hell we were in that map. So everything is offset. Now, there are a huge amount of applications for this technology. The first one that we all know of is Amazon's warehouses. They use this extensively to deliver and move products within the warehouse so that they're in the right places. The second one that I've mentioned is cleaning, but it's not just your little robots vacuums. It's also types of hazardous cleaning that you don't actually want a human being there for. The third one, and quite an ethical problem, is security robots and military applications. If something can figure out where it is and perform certain actions autonomously, it obviously raises a whole bunch of ethical questions. Hospitals can use it to deliver important things between the hospital, but it's not really used in hospitals due to their high entry cost. And typical exploration. For example, it can be used while exploring cave systems because humans can't fit into certain gaps. So how can you get involved? The first thing is an off-the-shelf robot. Turtlebot is a brand. They make lots of them, but they are fairly expensive, but they are really cool. The second way is to build it yourself, which is what I did. So you can build all the hardware, you can choose your own sensors, you can choose exactly how fast you want your robot to run. And then all the software is already there for you. These robots run on something called the Robot Operating System, which can do a whole bunch more than just SLAM, but it provides all the necessary tools that you need. So it is almost like a plug and play. And more than that, you can run the Robot Operating System on just about any Linux distro, and it comes with its own whole simulation suite. So on the bottom right, you can see we're simulating a little room with a robot with a 360-degree LiDAR. And on the left, you can kind of see the map that it's developing. So to close off, I just want to show a video of one of these Turtlebot robots in action. This is the most recent one, the Turtlebot 4. It's using, I think, a combination of LiDAR and visual sensors. This one's kind of designed to deliver things between units. As you can see, that's why there's the hat on top of it. And this is all happening in real time. So you need something significantly more powerful than a Raspberry Pi, typically a proper embedded system. But as you can see, the results are really impressive. And high-cost systems are much more fancy than this. There's a university in the States where this is one of their university modules. And what they do is the whole point of the module is to see how quickly you can develop this algorithm. So they actually race these robots because the mapping takes so long, it has a significant effect on how fast you can move. So you pass the module if you race fast. Yeah, cool. Thank you, everyone.